You know, if you were to just reach out right now and punch the wooden desk in front of you, or like maybe the steering wheel of your car or the kitchen counter you're leaning against.
You'd get a pretty immediate reality check.
Right, exactly. You would get
Yeah.
a very specific, very reassuring sensation. I mean, it hurts a little bit, sure, but it feels undeniably universally solid.
It pushes back.
Yeah, the wood pushes back against your skin, your knuckles stop moving. And for our entire lives, like literally from the moment we're born and start grabbing toys, we use that exact tactile feedback to build a mental map of reality.
We learn that things are solid.
Things are solid, they have distinct boundaries, they have a definite, unquestionable location in space. But what if I told you that every single ounce of that solidity, the very concept of a physical boundary, is a complete and utter cosmic illusion?
It really is the ultimate magic trick of the universe. I mean,
Yeah.
we spend our days navigating a world that feels like rigid architecture. But when you strip away the macroscopic scale and look beneath the surface...
Yeah, the really tiny stuff?
Exactly. When you look down there, it is actually something closer to a chaotic overlapping symphony. It's not architecture at all. It's music.
And that realization is exactly what we're going to explore today on this deep dive. Because there's this famous quote from the physicist John Archibald Wheeler, though, you'll actually often see it attributed to Niels Bohr.
Right. The quote about confusion.
Yeah, he basically said, if you are not completely confused by quantum mechanics, you do not understand it. And I have to admit, as we step into the materials for today, my brain is already hurting a little bit.
But in a good way, hopefully.
The best possible way. So the historical notes and concepts we're unpacking today cover what physicists refer to as the quantum mirage, and specifically the mind-bending concept of matter waves.
Which is just a wild concept to try and wrap your head around.
It really is. So our mission for you, listening today, is to completely strip away your everyday common sense intuition. We want to guide you through the honestly terrifying but beautiful truth that the solid universe, you, me, that desk you just punched, the stars in the sky.
All of it.
All of it. It's actually a stormy ocean of interacting waves.
Yeah, and it requires a really profound shift in perspective. To truly grasp what these concepts are telling us about reality, you kind of have to willingly let go of the idea that we're made of tiny, hard, billiard ball-like particles.
Which is hard to do.
Oh, it's incredibly hard. The history we're examining today takes us step by step through arguably the greatest conceptual revolution in human history. But to appreciate the magnitude of that shift, we have to understand the context.
Right. We can't just jump straight into the quantum realm.
No, because before we can understand how solid matter acts like a wave, we have to look at the absolute, centuries-long, brutal war over the nature of light.
Yeah, going through these notes, it seems like by the early 1920s, the global physics community wasn't just confused, they were in a state of, like, hair-pulling existential panic.
Panic is the exact right word for it. I mean, you have to imagine the foundation of everything these brilliant scientists believed was just violently cracking under their feet. For centuries, the absolute brightest minds on the planet could not agree on what light fundamentally was.
And it started with Newton, right?
Right, Isaac Newton. He was the undisputed titan of classical physics. I mean, if Newton said something, it was treated as absolute gospel.
And he had a very specific idea about light.
He did. Newton stubbornly insisted that light was a stream of tiny, solid, indivisible particles. He called them corpuscles.
Corpuscles, which is a great word, but why did he think that? I mean, light doesn't feel like a stream of physical objects hitting you. Why was he so convinced?
It was because of the way light behaves geometrically. Newton observed that light casts perfectly sharp shadows. It travels in absolute straight lines.
Okay, that makes sense.
Right. And if you shine a beam of light at a mirror, it bounces off at the exact angle you'd expect a rubber ball to bounce off a brick wall. It obeys the laws of mechanical reflection perfectly.
So it acts like a physical thing bouncing.
Exactly. So in Newton's mind, the only logical explanation was that light was made of microscopic physical cannonballs. And because Newton was so revered, his particle theory absolutely dominated the scientific consensus for a very long time.
Because it just felt intuitive.
Yeah, it felt deeply intuitive to a species that interacts with solid objects every day.
But then intuition hits a brick wall. Because along comes Thomas Young in the early 1800s. And Thomas Young completely wrecks Newton's elegant little particle theory with an experiment that is now legendary.
The double slit experiment.
Yes, the double slit. And from what I understand, he essentially shines a light through two narrow parallel slits cut into a barrier and lets that light hit a screen on the other side.
Right.
Now, if Newton was right, and light is a stream of tiny solid balls, you'd just expect those balls to fly through the two slits and create two bright lines on the back screen, like, spraying a hose through a fence.
Exactly. You'd expect a binary outcome, path A or path B.
But that is not what Young saw.
Not at all. When the light passed through the two slits, it didn't form two bands. It fanned out and created this complex pattern of alternating bright and dark stripes spreading across the entire screen. This is what we call an interference pattern.
Okay, let's unpack that for a second. Why do alternating bright and dark stripes prove that light is a wave? Like, how does that work?
Well, think about water. Imagine you're standing at the edge of a perfectly still pond, and you drop two pebbles into the water side by side at the exact same time.
Okay, I can picture that.
Each pebble creates a circular ripple, a wave that spreads outward. And eventually, the ripples from the left pebble are going to crash into the ripples from the right pebble.
Right, they overlap.
Yes, and when they overlap, two things can happen. If the high point of one wave, the crest, meets the crest of the other wave, they combine their energy and push the water even higher. They amplify each other.
And that's called constructive interference, right?
Exactly. Constructive interference. On Young's screen, this amplification creates the bright stripes of light. But if the crest of one wave happens to meet the low point, the trough of the other wave, they literally fight each other and cancel each other out entirely.
The water just becomes flat.
Perfectly flat. This is destructive interference. And on Young's screen, this cancellation creates the dark stripes, areas where light plus light somehow equals complete darkness.
Which is just an insane concept on its face. You shine a light, add another light, and you get a shadow.
It's completely wild.
But mathematically, it only works if light is rippling like water. It proved, beyond a shadow of a doubt, that light was definitively 100% a continuous rippling wave. Case closed, right? We can all pack up and go home. Newton was wrong.
Case closed until the year 1905.
Oh, of course.
Yeah, that is the year the ultimate scientific plot twist arrives, delivered by a young patent clerk named Albert Einstein.
I heard of him.
Just a little bit, right? So Einstein publishes his groundbreaking paper on the photoelectric effect. Scientists had noticed that if you shine light onto a piece of metal, the metal will occasionally spit out electrons.
It generates a tiny electrical current.
Right. Now, if light was just a continuous smooth wave, as Thomas Young proved, then shining a really bright, intense red light on the metal should eventually build up enough energy to wash those electrons away, like a massive ocean wave eroding a beach.
But that's not what happens.
Not at all. You can shine the brightest, most intense red light on certain metals for years and absolutely nothing happens. Zero electrons are knocked loose.
Wow.
But if you shine an incredibly dim, weak blue light on that same metal, electrons are instantly knocked violently off the surface.
Wait, hold on. Let me stop you there. Are you telling me the brightness of the light doesn't matter? Only the color?
Exactly.
How does that make any sense?
Well, it only makes sense if light is not a continuous smooth wave. Einstein realized that light was acting more like a hailstorm.
A hailstorm.
Yeah. He proved that light doesn't wash over the metal continuously. It hits the metal in discrete, localized, indivisible packets of energy. Think of them like microscopic energy bullets.
Oh, photons.
Yes, we now call these individual packets photons. A photon of red light just doesn't carry enough individual energy to knock an electron loose, no matter how many red photons you fire at it.
But a blue one does.
Right, a single photon of blue light hits like a sledgehammer.
So Einstein just resurrected Newton's corpuscles. He proved that light actually is a solid packet of energy, a particle.
He did.
Okay, I can totally see why the physics community was in a state of absolute panic. I mean, how can something be both a solid, indivisible packet and a continuous, spreading, rippling wave at the exact same time?
It's completely contradictory.
It really is. It's like dealing with a friend who constantly changes their personality depending on who they're hanging out with. If you test light with a double-slit experiment, it acts exactly like a water wave. If you test it with a piece of metal, it acts exactly like a stream of bullets.
The psychological toll this paradox took on the scientific community, it really cannot be overstated. You have an entire generation of the absolute brightest physicists who are rigidly trained to believe in absolute binary categories.
Wave or particle.
Exactly. In classical mechanics, something is either a wave, meaning it spreads out continuously through space and can overlap, or it is a particle, meaning it's a discrete, localized chunk of matter with a specific coordinate in space.
It cannot physically be both.
The definitions are mutually exclusive.
So when light was definitively proven to be both simultaneously, it wasn't just like a math problem. It was a crisis of logic. It felt like the universe was actively playing a prank on them.
It created a total theoretical deadlock. The old guard was trying to shoehorn this impossible duality into their existing classical framework, and it just wasn't fitting.
Right.
And historically, when an entire academic establishment is paralyzed by their own rigid rules, it perfectly sets the stage for a total outsider to walk in, look at the problem without any preconceived baggage, and just break the rules completely.
And what an outsider he was. This brings us to the arrival of a highly unlikely hero in our story. Someone who looks at this agonizing, unsolvable riddle about light and decides to flip the entire question right on its head.
Louis de Broglie.
Yes, let me introduce you to Louis de Broglie. And honestly, looking at his background in these notes, it is just absurdly perfect for a scientific revolution. Because he wasn't really a scientist at all. He was a literal French aristocrat. He was a prince.
He really was.
And initially, his area of study at university wasn't advanced mathematics or quantum physics. He was studying history and literature.
He was the absolute furthest thing from your standard, mathematically obsessed, chalkboard-staring physicist. He was a humanities scholar from a noble family.
But then World War I happened.
Right. His entire trajectory changed dramatically with the outbreak of the war. De Broglie was drafted, but instead of being sent to the trenches, he was stationed at the Eiffel Tower, serving as a radio operator for the French military.
Wait, so he spent the war literally sending invisible signals across battlefields?
Precisely. And that visceral, hands-on experience working with radio transmitters, visualizing these invisible waves carrying information through the air, it sparked a deep, almost obsessive fascination within him.
So he just starts reading physics.
He starts reading physics voraciously. And after the war, he completely pivots. He abandons his history track, goes incredibly deep into theoretical physics, and in 1924, he submits his PhD thesis to the Sorbonne in Paris.
And what a thesis it was. In this document, he proposes what our deep dive materials refer to as the de Broglie reversal. He looks at the utter chaos surrounding the nature of light. The fact that a rippling wave of light can somehow magically act like a solid bullet.
Right.
And instead of trying to solve that, he asks the most gloriously naive, audacious question imaginable. He asks, if a wave of light can act like a solid particle, why can't a solid particle like an electron or a baseball or a planet act like a rippling wave?
It's a breathtaking leap of intuition. What's fascinating here is he was essentially arguing for universal cosmic symmetry. He reasoned that nature loves balance. If nature allows this bizarre wave-particle duality to exist for light, why wouldn't it mandate the exact same duality for all physical matter in the universe?
I just love imagining the faces of his examining committee when they read this. I mean, you have to put yourself in their shoes. They are prestigious, serious physicists, and they're reading a thesis from a former history major who is casually suggesting that the chair they are sitting on is actually vibrating like a pool of water.
They were absolutely stunned.
And probably not in a good way.
No, they genuinely thought he might have lost his mind. They were deeply conflicted. On one hand, the mathematics he used to construct his argument were internally consistent.
The math worked.
The math worked. But on the other hand, the physical implication was so absurd that they were afraid to approve it. I mean, they didn't want to fail a literal prince and cause a scandal, but they also couldn't put the Sorbonne stamp of approval on a thesis that sounded like a hallucinogenic fever dream.
So what did they do?
They did what terrified academics always do. They kicked the can down the road. They sent a copy of his thesis to the one person on Earth who had enough authority and enough of a reputation for radical thinking to tell them what to do with it.
Einstein.
They sent it to Albert Einstein.
And Einstein's reaction to this is just incredible. He reads de Broglie's work, completely bypasses the absurdity of it, and instantly recognizes the profound, terrifying genius hidden in the math.
Yes, he does.
He writes back to the examining committee in Paris, and his message is completely unequivocal. He essentially tells them, give this man his PhD immediately. He has lifted a corner of the Great Veil.
It's such a beautiful endorsement. Einstein, who had broken reality himself by proving light was a particle, saw that de Broglie had just completed the circle.
Wow.
Einstein understood that this wasn't just some clever mathematical parlor trick.
Yeah.
It was a fundamental, terrifying truth about the mechanics of reality. Matter and energy were playing by the exact same bizarre rules.
And here's where it gets really interesting. The vindication is incredibly swift, because just 5 years later, in 1929, Louis de Broglie, the history major, the radio operator, the prince, is awarded the Nobel Prize in physics.
Yes.
He becomes the very first person in the history of the award to win a Nobel Prize for a PhD thesis. He essentially single-handedly birthed the field of wave mechanics and kicked the door to the quantum realm wide open.
He really did.
But, as we know, proposing an absurd, universe-breaking idea is one thing. Actually proving it mathematically is another. So we have to dive into the equation that bridged these two contradictory worlds, the de Broglie wavelength.
We do. But before we break down the variables of that equation, we have to clarify a very crucial distinction about what we mean when we say matter waves.
Okay, what's the distinction?
Because when you hear that phrase, it's very easy to picture an electron bobbing up and down, surfing on top of some invisible quantum ocean. Up until this point in history, whenever scientists talked about a wave, they were always talking about a disturbance traveling through a physical medium.
Right. Like if I yell across the room, the sound wave is just a pressure shutter traveling through the air. The air is the medium.
Exactly.
Or if I drop a rock in a pond, the wave is energy moving through the water. The water is the medium. Even gravitational waves are ripples passing through the fabric of space-time itself. The wave is an event. It's something that happens to the medium.
That's the classical view, yes. But de Broglie's matter waves are fundamentally ontologically different. There is no background ocean.
Wait, really?
Really.
All right.
There is no hidden quantum ether that the particle is rippling through. When we say an electron acts like a wave, we mean the electron is the wave. Its very physical existence is smeared out into a rippling probability distribution.
Okay, my brain is officially starting to hurt. The object itself is a ripple.
Yes.
But the math he provided to prove this is actually stunningly simple, right? It's known as the cosmic code. The equation is lambda equals h over p, wavelength equals Planck's constant divided by momentum. Let's really break this down for you listening, because every single piece of this tiny equation tells a massive story about reality.
Let's start with the structure of the equation itself. On the left side of the equal sign, you have the Greek letter lambda. In physics, lambda exclusively represents wavelength, the distance between two crests of a wave.
Got it.
So the entire left side of this equation belongs strictly to the ethereal world of waves, ripples, frequencies, and continuous fields.
And then on the right side, in the denominator of the fraction, you have the letter p.
Yes.
In physics, p stands for momentum, which is simply an object's mass multiplied by its velocity, how heavy it is and how fast it is moving. And mass belongs strictly to the world of solid, physical, tangible particles. You can't have mass without being a physical object.
Exactly. And resting right between them, acting as a bridge between two seemingly incompatible dimensions of reality, is the equal sign. De Broglie was stating unequivocally that the wavelength of an object is inversely proportional to its momentum.
The world of waves and the world of solid matter are mathematically identical.
But the true secret to this equation, the reason the universe behaves the way it does, lies in the numerator of that fraction, the letter h.
Planck's constant.
Yes, Planck's a constant. Max Planck discovered this constant when he was studying how heat and light are emitted. It is the fundamental number that dictates the scale and the graininess of the quantum world.
And it is an impossibly comically tiny number. The value of Planck's constant is 6.626 times 10 to the negative 34th power joule seconds. For those trying to visualize that, that is a decimal point, followed by 33 zeros, before you finally get to the numbers 6, 6, 2, 6.
Unimaginably small.
It really is. I love this analogy we've discussed before from the tips section, trying to visualize Planck's constant as the ultimate pixel size of the quantum universe.
That is a highly effective way to think about it. It represents the absolute foundational limit of how smoothly energy can flow or how finely action can be divided.
Right. So think about sitting on your couch staring at a massive, high-end 4K TV screen. When you watch a movie from the couch, the image looks perfectly smooth. A blue sky smoothly transitions into a white cloud. The colors blend perfectly.
It looks continuous.
It looks like a continuous, unbroken reality. But if you walk right up to the television and literally press your eyeball against the glass, the illusion breaks. You realize the image isn't smooth at all. It is constructed from millions of rigid, tiny, distinct, indivisible square pixels, a discrete grid of red, green, and blue lights.
And our reality is no different. The universe only looks completely smooth and continuous to us because the pixels of reality dictated by the incredibly tiny value of Planck's constant are so unimaginably small that our macroscopic human senses could never possibly detect the jagged, pixelated nature of the quantum grid.
So we have this tiny pixel size h sitting on top of the fraction, and we have the physical momentum of the object sitting on the bottom. Let's talk about the math of that relationship, because momentum being in the denominator is the crucial key here.
It is. If we connect this to the bigger picture, mathematically, a fraction is just division. You are taking the top number and dividing it by the bottom number.
Right.
If the number on the bottom, the denominator, gets larger, the final result of the equation gets smaller. If you divide a pizza into 4 slices, the slices are big. If you divide it into 100 slices, the slices are tiny.
Okay, I follow.
So if an object has a very large momentum, meaning it is either very heavy, very fast, or both, you're dividing Planck's constant by a very large number.
Which means the resulting wavelength, lambda, becomes incredibly small.
Exactly. The heavier or faster an object is, the tighter, smaller, and less noticeable its wave nature becomes.
Which perfectly transitions into applying this terrifying math to our everyday human lives. Because I know exactly what you're thinking as you listen to this. You're sitting there looking at your hands thinking, if this equation governs the entire universe, if literally every physical object with mass has a wavelength, why don't I notice it?
It's the obvious question.
Right, like why don't you wiggle and ripple when you walk down the street? If you're a wave, why don't you diffract and spread out into a cloud of probability when you walk through your bedroom doorway?
It is the most natural, intuitive question to ask. And to answer it, we don't need philosophy. We just need to plug a human being into de Broglie's equation.
Let's do the math.
Let's do it. Let's say you have an average mass of about 70 kilograms. And let's say you are walking down the street at a leisurely pace of 1 meter per second. Your momentum mass times velocity is 70.
Okay, momentum is 70.
Now plug that into the cosmic code. Wavelength equals Planck's constant divided by momentum. You take h, that ridiculously tiny number with 33 zeros after the decimal point, and you divide it by a relatively massive number like 70.
And the result is a wavelength that is so microscopic, so incredibly tiny that it is functionally zero.
Functionally zero.
The math literally works out to a wavelength that is billions of times smaller than a single solitary proton inside an atom. You physically couldn't measure a wave that small if you tried.
You really couldn't.
So from a macroscopic perspective, standing here in the everyday world, your wave nature is completely, utterly erased by your massive 70-kilogram bulk. You don't wiggle through doorways because your wave is too tightly bound. You act like a solid, predictable, classical piece of matter. The illusion of solidity holds up.
Precisely. You are experiencing the macroscopic mirage. But to see the reality, we have to contrast your massive human body with something from the quantum realm. Let's look at an electron.
Okay.
The mass of a single electron is roughly 9.11 times 10 to the negative 31st power kilograms.
So basically weightless. Another absurd decimal with 30 zeros.
Yes. Now, if you plug that unbelievably tiny mass into the bottom of the fraction, suddenly you're no longer dividing by a massive number like 70.
Right.
You're dividing Planck's constant by a number that is nearly as impossibly small as Planck's constant itself.
Yeah.
And when you divide a tiny number by another equally tiny number, the result is suddenly a significant measurable value.
The fraction balances out.
Exactly. Because the electron's mass is so utterly insignificant, its wavelength becomes highly significant. It isn't functionally zero anymore. Its wavelength becomes large enough to interact with its physical environment.
Oh, wow.
When an electron moves through space, it doesn't fly like a tiny solid bullet. Its wave nature completely dominates its physical presence. It smears out, it vibrates, it loses its defined location, and becomes a literal blur of probability.
You know, hearing it broken down like that, it actually explains a huge historical blind spot that physicists had. Like, why did brilliant minds like Galileo and Newton, who were obsessively studying motion, completely miss the fact that matter acts like a wave?
That's a great point.
Why did it take until the 1920s to figure this out? And the answer is just plain mass. When Galileo was dropping cannonballs off the Leaning Tower of Pisa, or Newton was swinging huge pendulums, those objects were far, far too massive.
The momentum was huge.
Right. The wavelengths of those iron cannonballs were so unimaginably small that there was absolutely zero detectable wave behavior. Their own human scale blinded them. They were trapped inside the macroscopic mirage.
It is a profound example of how our specific scale in the universe limits our perception of reality. We, as biological organisms, evolved to interact with heavy, slow-moving objects, rocks, trees, predators.
Right?
So our human brains developed an intuition based entirely on classical physics. We expect things to be solid. The quantum blur was completely invisible to us until our technology finally allowed us to probe the subatomic scale.
Wait, hold on. Working through this math just triggered a sudden realization for me, a genuinely weird thought.
What's that?
If my wavelength is Planck's constant divided by my mass times my velocity, mathematically speaking, if I'm walking down the street and I suddenly start dead sprinting as fast as I can, my velocity goes up, which means my momentum, the bottom number of the fraction, goes up.
That's correct.
So since momentum is in the denominator, dividing by a larger number means my resulting wavelength gets even smaller. So wait, by running, I am physically making my personal wavelength shorter.
You are.
I become even less wave-like and even more solid and particle-like the faster I move.
That is exactly right. The faster you move, the tighter your quantum wave becomes. By increasing your momentum, you're effectively suppressing your wave nature even further.
That is just wild to think about. I am literally shifting my quantum state by jogging.
It's wonderfully counterintuitive.
Yeah.
In the macroscopic world, we associate high speeds with a blur. But in the quantum world, high momentum mathematically sharpens the particle, defining its location more rigidly.
Unbelievable. But okay, as fascinating as this is, theory and math are fantastic on a chalkboard. They make for great thought experiments. But in physics, beautiful math essentially means nothing without cold, hard physical proof.
Right, you need experimental data.
And our sources do not shy away from how physicists actually went about proving this probability blur. We have to move out of the theoretical chalkboard and into the laboratory, into an experiment that completely broke our understanding of reality.
The double slit experiment performed with solid matter.
Yes. This is the exact moment where the abstract, elegant math of de Broglie crashes violently into physical reality. To truly appreciate how shocking the results of this experiment are, we first have to establish a clear control using the classical physics of our everyday world.
Okay, let's paint the picture.
Imagine a setup similar to Thomas Young's light experiment, but scaled up. You have a barrier with two vertical slits cut into it. Behind that barrier is a blank canvas. And instead of shining a light, imagine you are holding a paintball gun. You are firing solid, physical, macroscopic paintballs at the barrier.
Right, so you stand back and you unleash a barrage of paintballs. They fly through the air as solid projectiles.
Exactly. Some of them hit the wall between the slits and splatter, bouncing off. But some of them fly cleanly through slit A, and some of them fly cleanly through slit B. Over time, as those paintballs travel through the slits and hit the canvas in the back, what do I expect to see?
Two bands.
I expect to see two distinct, messy, vertical bands of paint. Two stripes corresponding to the two open doors. Because that is how solid matter behaves. It is binary. A paintball takes one path or it takes the other path. It cannot physically go through both slits at once.
Perfect. That is our classical expectation. Now, we perform the exact same experiment, but we scale it down to the quantum level. We swap the macroscopic paintball gun for a subatomic electron gun.
Okay.
We know electrons have mass. We can weigh them. We know they are fundamental physical pieces of matter. So we fire a continuous high-speed beam of these microscopic paintballs toward a barrier with two incredibly narrow microscopic slits.
And if we apply our everyday logic, if electrons are just tiny paintballs, the expectation is entirely straightforward. We should see two distinct bands of electron impacts build up on the detector screen in the back.
But the result is anything but straightforward. The physicists run the experiment, they look at the detector screen, and they don't see two bands.
What do they see?
They see a sprawling, barcode-like pattern of alternating bright and dark stripes spreading across the entire screen.
No way.
Yes. It is a classic, undeniable interference pattern. The exact same pattern Thomas Young saw when he shone a light through the slits.
That is, to understand why this is so impossible, we have to look back at our pond analogy. The bright stripes on the screen represent areas where many, many electrons are hitting.
Which corresponds to the crest of one wave amplifying the crest of another wave. Constructive interference.
Yeah. Right. But the dark stripes the gaps in the barcode, where essentially 0 electrons hit, represent destructive interference. Areas where the crest of one wave perfectly met the trough of another wave, canceling out the probability of an electron landing there entirely.
Exactly. Let that sink in for a second because it is staggering.
Yeah.
The electrons, which are physical pieces of matter, did not fly through the slits like solid bullets.
The beam of electrons acted exactly like a wave of water.
Yes. The wave hit the barrier, split into two separate ripples, passed through both slits simultaneously, and then those two newly formed ripples crashed into each other on the other side, amplifying and canceling each other out, deciding where the electrons were allowed to hit the screen.
It's profound. But, physicists are a naturally skeptical bunch. When they saw this interference pattern, they didn't immediately accept that reality was broken.
Oh, of course not. They searched for a classical explanation. They thought, okay, a beam of electrons contains billions of particles. Maybe we're firing too many electrons at once.
Right, they have negative charges, so they repel each other.
Exactly. Maybe as they squeeze through the slits, they're literally bumping into each other midair, ricocheting and bouncing off each other like a chaotic break in a game of pool, and scattering into this weird barcode pattern.
Which is a perfectly reasonable assumption. I mean, it preserves sanity. So to test this, they changed the parameters of the experiment. They decided to eliminate the possibility of midair collisions entirely.
How do they do that?
They take the electron gun and they dial it all the way down. They slow the emission rate down so drastically that the gun fires exactly one single solitary electron at a time. Click. One electron is fired. It travels through the vacuum chamber. It hits the screen. We wait. Click. Another single electron is fired.
It leaves the gun as a single indivisible particle.
Yeah.
And when it hits the detector screen, it hits as a single, precise, localized dot. There's absolutely no other electron in the chamber for it to bounce off of. There is no chaotic game of pool happening.
So they run this painfully slow version of the experiment. They fire thousands, millions of these single electrons, one by one, over the course of several hours.
And they watch the screen.
Yeah, they watch the screen. First, a random dot appears on the left, then a dot on the right. It looks like random static at first, but slowly, dot by agonizing dot. The exact same alternating barcode pattern builds up on the screen.
It's an outcome that absolutely defies and shatters all classical logic.
It really does.
Think about the implications. If a single electron is fired into an empty chamber and its final landing position is dictated by an interference pattern, it must be interfering with something.
But there is no other electron there.
Exactly. As the physicist Erwin Schrodinger argued, the only mathematical conclusion is that the electron itself is not a tiny point of matter. It is a spreading wave of probability, described by a complex mathematical formula known as the wave function, represented by the Greek letter psi.
Wait, hold on. Let me make sure I am grasping the sheer madness of what you were saying. Are you telling me that a single solitary particle goes through both slits?
Yes. Richard Feynman, another brilliant theoretical physicist, took Schrodinger's math even further with his concept of sum over histories. Feynman showed that in quantum mechanics, a particle doesn't just take one path. Between the moment it leaves the gun and the moment it hits the screen, the particle literally takes every single possible path available to it in the universe simultaneously.
Every possible path, meaning it goes through slit A, it goes through slit B, goes through neither, it loops around Jupiter and then goes through the slit.
Mathematically, yes.
They're insane.
Most of those extreme paths cancel each other out in the probability math. But the dominant paths going through slit A and going through slit B remain.
Okay.
When that single electron leaves the gun, it travels through the vacuum chamber, not as a solid physical object, but as an expanding wave of pure, unadulterated probability.
So it's a cloud.
A probability cloud. That wave encounters the physical wall. A portion of the wave passes through slit A, and a portion of the exact same wave passes through slit B at the exact same time. It emerges on the other side as two overlapping probability waves.
And they interfere with each other.
Those waves interfere with each other, calculating the mathematical odds of where the electron should exist. And then, the very instant the wave touches the detector screen,
The probability collapses.
exactly, the wave instantly vanishes from everywhere else in the universe, and the electron randomly snaps back into reality as a solid, measurable, tangible particle, leaving a single dot of light on the screen.
So to summarize this absolute insanity, the particle essentially ghosted itself.
You could say that.
It leaves the gun, splits its own existence into a ghostly cloud of maybe, goes through two separate doors at the same time, physically fights with its own shadow on the other side, and then decides to be a solid physical object again only at the exact moment it hits the back wall.
That's a very accurate summary.
It is sheer, unadulterated madness. How do physicists even sleep at night knowing this is how the universe works?
It definitely keeps them up. Because this raises an important question. What does the word location even mean at the quantum level?
Right. Does here even exist?
Exactly. Our entire classical definition of location, the reassuring idea that an object has a definite here or there at all times, Even when we aren't looking at it, it entirely breaks down. Before the electron hits that detector screen, asking, where's the electron, is a fundamentally invalid question.
Because it's everywhere.
It doesn't have a single location. It has a distribution of probabilities. It exists everywhere and nowhere all at once until an interaction forces it to choose.
It is just staggering to try and visualize. But, as we move through these materials, it becomes incredibly clear that this wave-particle duality isn't just some weird, abstract parlor trick that only happens when scientists set up sterile vacuum chambers in laboratories.
No, not at all.
This isn't just an anomaly. This transition from laboratory weirdness to absolute existential necessity is where this deep dive gets really profound. Because we have to talk about the chemical consequences of the mirage. This exact phenomenon, this impossible probability blur, is the sole reason you, listening to this right now, physically exists.
It's absolutely true. To understand why wave mechanics is the foundation of your existence, we have to look away from the double-slit experiment and look directly at the internal structure of the atom itself.
The atom.
Yeah. If you think back to the basic chemistry or physics classes you took in school, you were almost certainly taught the classical planetary model of the atom.
Oh, absolutely. The classic, iconic logo for anything science-related. The Jimmy Neutron atom.
Exactly.
You have a dense nucleus of protons and neutrons sitting in the dead center, and you have these tiny electrons zipping around it in nice, neat little oval orbits. It looks exactly like the planets orbiting the sun in our solar system. Gravity holds the planets in, electromagnetism holds the electrons in. It makes perfect sense.
It's a very visually comforting, intuitive image. But as the theoretical physicists of the early 20th century realized, there is a fatal, catastrophic flaw in that planetary model.
What's the flaw?
The laws of classical physics, specifically James Clerk Maxwell's equations of electromagnetism, dictate a very strict rule. Any electrically charged particle that is moving in a circular path is constantly changing its direction. And a constant change in direction means the particle is constantly accelerating.
Wait, even if it's moving at a steady speed, moving in a circle is technically acceleration.
Correct. And Maxwell proved that an accelerating electrical charge must radiate energy away in the form of electromagnetic waves, like light or heat.
Okay, wait. Let me connect the dots here. If an electron is a tiny, solid, negatively charged planet orbiting the nucleus, it is moving in a circle. Therefore, it is accelerating. Therefore, it must constantly be bleeding off its own energy in the form of light.
Yes.
But if it loses energy, it loses speed. It loses its ability to fight the electromagnetic pull of the nucleus, so the orbit would shrink. It would start to death spiral inward.
And it would do so incredibly fast. Calculations showed that if classical physics ruled the atom, an electron would radiate all its energy and death spiral into the nucleus in a tiny fraction of a second, roughly 10 to the negative 11 seconds.
Oh my God.
The positive and negative charges would crash into each other. If the planetary model were true, every single atom in your body, every atom in the Earth, and the entire physical structure of the universe would instantly collapse into itself. The universe would be over before it even started.
Wow. Okay, so the fact that I am sitting here right now proves the planetary model is wrong.
Pretty much.
But what prevents this instant collapse? Why don't the electrons crash into the nucleus?
This is where Louis de Broglie and his absurd wave theory swoop in to save the day, right?
Exactly. The electron doesn't death spiral because it isn't a solid planetary sphere at all. When an electron gets trapped in the electromagnetic gravitational pull of an atomic nucleus, its matter wave fundamentally alters.
The probability blur smears out, stretches, and wraps completely around the central nucleus. It ceases to be a point-like particle flying through space, and it becomes what physicists call a standing wave.
A standing wave. The materials offer a really beautiful analogy for this, comparing it to plucking a guitar string.
It's a great analogy.
Yeah, like when you press down on a fret and pluck the string of a guitar, the string vibrates violently up and down. But the ends of the string are physically pinned down, one end at your finger, the other end at the bridge of the guitar.
Right.
Because the ends are fixed, the mechanical wave travels down the string, hits the solid end, and reflects back on itself perfectly. It forms a stable, vibrating wave pattern that oscillates rapidly up and down, but the weight itself doesn't travel horizontally across the room. It stays in one place.
That is a perfect visualization. The trapped electron acts exactly like that plucked guitar string. But instead of being stretched in a straight line, the string is wrapped into a continuous circle around the nucleus.
Okay, I can picture that.
And this conceptual shift leads directly to the most important concept in modern chemistry: Quantization.
Quantization. How so?
Just like a guitar string can only play certain specific notes based on its exact physical length, an electron's probability wave can only exist around a nucleus if it forms a perfectly stable, continuous standing wave.
Okay.
For that to happen, the circumference of its orbit must perfectly match a whole, round, integer number of its wavelengths. 1 complete wavelength, 2 complete wavelengths, 3 complete wavelengths, and so on.
Right. If the circumference of the orbit is exactly, say, 3 wavelengths long, then as the wave completes its orbit around the nucleus, the end of the wave connects perfectly seamlessly with the beginning of the wave.
Exactly.
The crests line up with the crests, the troughs line up with the troughs. It reinforces itself through constructive interference. It creates a stable, infinite loop of probability.
But let's play out the alternative. What happens if the electron tries to exist in an orbit where the math doesn't match perfectly? What if the wave wraps around the nucleus and the circumference of that specific distance happens to be exactly 2.5 wavelengths long?
Well, if it's 2.5 wavelengths long, then as the wave completes its first orbit and starts its second lap around the nucleus, it's going to be completely out of sync.
Right.
The crest of the second lap will perfectly overlap with the trough of the first lap. They will be exactly out of phase. And just like the dark stripes we saw in the double slit experiment, the wave will interfere with itself. It will cancel itself out of existence. It literally destroys its own probability.
Exactly. And because it destroys itself, that specific orbit, that specific distance from the nucleus, is what physicists call mathematically forbidden.
Mathematically forbidden. I absolutely love that phrase. It sounds like a spell from a fantasy novel or a sci-fi movie title.
It really does.
But it carries such profound weight. It means that the electron literally, physically, cannot exist in that space. It isn't just unlikely, it is impossible. It can only exist at the very specific, quantized distances where its wave perfectly connects with itself.
The spaces between those allowed orbits are dead zones. An electron can exist on step 1 of the staircase, or step 2, but it cannot exist floating in the air between the steps. These specific allowed standing waves are what chemists call quantized energy levels.
And we have to remember that we live in a three-dimensional universe. These standing waves aren't just flat two-dimensional hula hoops circling the nucleus. They balloon out into incredibly complex, beautiful three-dimensional probability clouds.
Yes, the orbitals.
Right. We refer to these clouds as the S, P, D, and F orbitals. The basic S orbital is a simple sphere of probability around the nucleus. But the p orbital looks like a three-dimensional dumbbell. The d and f orbitals look like complex four-leaf clovers or bizarre twisting balloons.
And these intricate, mathematically rigid geometric shapes are entirely dictated by the rules of wave interference, by how the wave can fold around the nucleus in 3D space without canceling itself out.
Okay, I have to push back a little here. I need to try and square this circle because it feels like a massive paradox.
Go for it. What's the paradox?
We started this section talking about the electron as this completely chaotic, unpredictable blur of probability, a smeared-out cloud of maybe that goes through two doors at once and defies all logic. But now you're telling me that this exact same chaotic, fuzzy blur is entirely responsible for the incredibly rigid, predictable, unbreakable rules of chemistry.
Yes.
The strict rules that dictate exactly how two hydrogen atoms bond with an oxygen atom at a precise angle to make a water molecule, or how millions of carbon atoms link together in a perfect sequence to form the DNA in my cells. How does quantum chaos create such perfect, reliable, macroscopic order?
It's a brilliant paradox, and it is the absolute heart of physical chemistry. The rigidity of our world doesn't come from atoms being tiny, solid building blocks. The rigidity comes exclusively from the geometry of these standing waves.
The geometry.
Because an electron is a wave, and because it can only exist in these very specific, mathematically allowed, quantized 3D shapes, atoms can only interact with each other in very specific, geometrically precise ways. The rigid shapes of these 3D standing waves dictate exactly how atoms lock together.
Oh, so they fit together like microscopic puzzle pieces.
Exactly. If the geometric shape of the probability wave of atom A doesn't align perfectly with the geometry of the probability wave of atom B, they cannot share electrons. The chemical bond is mathematically forbidden from forming.
Wow.
So the ironclad, unbreakable rules of chemistry that build mountains, oceans, and human bodies are actually just a macroscopic manifestation of subatomic wave interference. The rigid, solid, physical structure of our universe is dictated entirely by a vibrating quantum mirage refusing to cancel itself out.
That is just phenomenal. To think that the comforting solidity of the ice clinking in my drink or the complex roaring structure of a star is just a byproduct of these subatomic waves perfectly harmonizing with each other. It is physical poetry.
It really is beautifully poetic.
But as mind-expanding as this theory is, we need to ground it. We need to move beyond the chalkboard, beyond the abstract philosophical theory, because our sources do an amazing job of connecting this bizarre quantum math to astonishing, tangible, real-world technologies.
Yes, things that you, listening right now, interact with, rely upon, and take for granted on a daily basis.
It's a crucial pivot. We have to realize that quantum mechanics and wave-particle duality aren't just abstract philosophical frameworks for academics to debate. They are practical engineering blueprints.
They absolutely are. Once humanity understood the de Broglie equation, once we understood that we could manipulate the wavelength of matter by altering its momentum, we started exploiting it to build the modern world.
And a perfect, clear example from our materials is the invention of the electron microscope. This blew my mind. Because the obvious question is, if atoms are so small, why can't we just use regular visible light to see them? We have incredibly powerful lenses. We can see distant galaxies. Why can't we just polish a glass lens perfectly enough to zoom in infinitely and look at a single atom of gold?
Well, the materials use an analogy to explain this that I absolutely love.
The snow glove analogy.
Yes. Trying to see an individual atom with visible light is like trying to feel the microscopic grooves of a vinyl record while wearing thick, heavy winter snow gloves.
It's an incredibly apt analogy. The limitation isn't the quality of the glass lens. The limitation is the physical size of the light wave itself.
Exactly. Visible light that light our eyes can see has a wavelength of roughly 400 to 700 nanometers. In the everyday world, that seems incredibly small, but down in the quantum realm, a wavelength of 400 nanometers is massive. It's gigantic, clumsy, and blunt.
Correct.
If you try to illuminate something as unimaginably tiny as a single atom using a wave of visible light, the light wave just washes completely over the atom without even noticing it. Much like a massive ocean swell passing smoothly over a tiny grain of sand on the seafloor, the wave doesn't interact with the object.
The snow glove is simply too thick and clumsy to dip down into the tiny groove of the record. You cannot physically resolve an image of an object if that object is smaller than the wavelength of the light you are using to illuminate it.
Exactly. But because Louis de Broglie gave us the cosmic code lambda equals h divided by momentum, we realized we had a loophole. We know that if we give a particle a massive amount of momentum, we can shrink its wavelength down to an incredibly tiny size.
So scientists realized we don't need to use light to take pictures. We can use electrons.
Which sounds crazy, right? Taking a photograph using physical matter instead of light?
It does, but mathematically it's flawless. Scientists built massive machines that use magnetic fields to accelerate beams of electrons to incredibly high speeds, a significant fraction of the speed of light.
And by jacking up the velocity, they drastically increase the momentum.
Right. And as momentum skyrockets, the de Broglie wavelength of the electrons shrinks down to a fraction of a nanometer. They essentially swapped out the thick, clumsy winter snow glove for a microscopic, razor-sharp diamond needle.
And instead of shining light on a sample, they shoot these tiny, high-momentum electron waves at it. The resulting resolution is so breathtakingly sharp that they can take actual, literal photographs of individual atoms.
They can map the complex geometric structures of individual viruses. Our entire modern understanding of molecular biology, genetics, and materials science relies on exploiting the matter wave of the electron.
It's just brilliant engineering.
But the technological applications get even more intimately integrated into our daily lives when we look at a bizarre quantum phenomenon called quantum tunneling.
Oh, this is a great one.
This concept brings us right back to the idea of the electron acting as a smeared-out wave of pure probability. Because the electron isn't a solid physical point, but a fuzzy cloud of maybe, that probability wave function doesn't just hit a solid barrier and abruptly stop.
No, it doesn't. In classical physics, if you throw a tennis ball at a thick brick wall, the ball bounces back. If the ball doesn't have enough kinetic energy to physically smash through the wall or climb over it, it stays on this side of the wall. Full stop. The probability of the ball ending up on the other side of the wall is exactly zero.
Makes sense.
But in the quantum realm, because the electron is a wave of probability, when that wave hits a microscopic physical barrier, the wave doesn't violently terminate. It technically tapers off exponentially. The wave literally leaks into, and sometimes entirely through, the solid barrier.
Wait, so if an electron hits a microscopic solid wall that it doesn't have enough energy to cross, there is still a mathematical probability, a tiny chance that the wave extends past the wall.
Yep.
And because the wave is the electron, sometimes the electron just magically, instantaneously pops into existence on the other side of an impenetrable solid barrier. It literally ghosts right through a solid wall like a phantom.
Is the ultimate quantum cheat code. And this isn't science fiction, you know. It's a fundamental mechanism of the universe. In fact, it's the only reason the sun shines.
Really? The sun?
Yeah. In the core of our sun, you have countless hydrogen protons smashing together. Because they are all positively charged, they fiercely repel each other electromagnetically. Based on the temperature of the sun, they shouldn't actually have enough kinetic energy to overcome that repulsion and fuse together.
That shouldn't work.
But it does.
Yeah.
But it does, because of quantum tunneling. Their probability waves leak into each other through the electromagnetic barrier, allowing them to fuse, release massive amounts of energy, and power our entire solar system.
Okay, powering the sun is impressive. But the application of quantum tunneling that absolutely floored me in these notes was the connection to my smartphone. You were telling me that the mundane, everyday photos I take, the selfies I save on my phone, are physically stored on a silicon chip using a quantum probability leak. How on earth does that work?
It is a marvel of modern engineering. The flash memory inside your smartphone, or the solid-state drive in your laptop, functions by trapping millions of electrons inside microscopic cages.
Cages?
Yeah, these cages called floating gates are completely surrounded by an impenetrable layer of insulated material. An electron cannot physically cross that insulator. But when you hit save on a photo, the phone circuitry applies a very specific, sharp pulse of voltage to the system.
And what does that voltage do? Does it blow a hole in the cage?
No, it doesn't break the cage. The voltage temporarily distorts the shape of the insulating barrier, essentially making the wall just thin enough that the electron's probability wave can leak through to the other side. The voltage encourages the electron to quantum tunnel through the impenetrable insulator and materialize inside the cage.
And then what?
Once the voltage is removed, the barrier thickens again, and the electron is permanently trapped in the floating gate, representing a binary dark of data. To erase the photo, the phone applies a reverse voltage, coaxing the electron's wave to tunnel back out, resetting it to a zero WIMP.
That is just absurd. Our entire modern information age, every text message, every saved photo, every downloaded app is entirely built on scientists intentionally exploiting the ghostly probability blur of matter waves. Every time I swipe through my camera roll, I am quite literally looking at the macroscopic result of billions of localized, controlled quantum tunneling events. I will absolutely never look at my phone the same way again.
It definitely changes your perspective.
It really does. And before we move into the philosophy of all this, our sources outline one more beautiful, visual, everyday example of quantum mechanics: neon signs and fireworks.
Ah, yes.
We see those vivid, piercing reds, bright blues, and vibrant greens illuminating our cities at night. And according to the physics, what we are actually seeing with our naked eyes is the visual fingerprint of electrons changing their wave state.
Exactly. This brings us back perfectly to the concept of standing waves and quantized orbits.
Yeah.
We established that an electron can only exist in very specific, allowed wave shapes around the nucleus.
Mm.
Normally, an electron prefers to sit in the lowest energy orbit possible, close to the nucleus. We call this the ground state.
Okay, ground state.
But if we forcefully pump that atom full of extra energy, like by shooting high-voltage electricity through a tube of neon gas, or by violently heating up copper powder in an exploding firework, the electron absorbs that energy.
And it gets excited.
It gets excited, and it instantly leaps up into a larger, more complex, high-energy standing wave orbit.
But it doesn't want to stay there, right? It's inherently unstable. It wants to relax back down to its comfortable ground state.
Yes. And when it inevitably drops from that massive high-energy standing wave back down to the smaller low-energy standing wave, it faces a mathematical problem. It has too much energy for its new orbit.
So it has to get rid of it.
It has to get rid of the exact, precise difference in energy between those two specific orbits. And it ejects that exact, discrete packet of energy into the universe as a single photon of light.
A photon. We're back to Einstein's packets of light. And because those orbits are strictly quantized, because the geometric steps of the atomic staircase are always the exact same height, the energy difference is always exactly the same, which means the ejected photon always has the exact same frequency, which means it is always the exact identical color of light.
The distinct, fiery, glowing red of a neon sign is just billions of neon electrons dropping down the exact same quantum staircase simultaneously.
That is so cool.
The brilliant, searing green of a firework is copper electrons dropping down a different, specifically sized staircase. Even the specific barcode-like spectral lines that astronomers use to identify what distant galaxies and exoplanets are made of, all of it is just macroscopic visual evidence of subatomic matter waves dropping from one mathematically allowed geometry to another.
It is visual poetry. The math is literally painting the universe.
Yeah.
But as we move toward the final section of our deep dive today, we have to pivot.
We do.
We've established the mechanics, we've talked about the equation of the blur, the absolute madness of the double slit proof, the geometric rules of chemistry, and the technology in our pockets.
Yeah.
But we must confront the deep, lingering philosophical questions raised by this reality, because you simply cannot shatter the fundamental architecture of reality and not ponder what it means for our existence.
You really can't. The philosophical implications of the quantum mirage are profoundly unsettling, and they have triggered debates that have raged for a century.
And the materials invite us to ponder several different avenues, starting with perhaps the most famous, most debated, and most controversial concept in all of quantum physics: the observer effect.
The observer effect.
To understand this, we have to mentally revisit the double slit experiment. We established that when we fire a single electron into an empty chamber, its probability wave goes through both slits simultaneously, interferes with itself, and builds a barcode pattern on the back wall.
Right. It acts exactly like a wave when no one is watching.
When no one is watching is the key phrase here, because physicists, being naturally curious, wanted to know how the wave was splitting. They wanted to know which slit the bulk of the electron actually passed through. So they changed the experiment again. They set up a detector, essentially a microscopic camera, or a sensor right at the slits to observe the electron as it passed through. They wanted to catch the probability wave in the act of splitting.
And what happened when they turned the camera on?
This is the crazy part. The moment they turned the detector on, the moment they recorded the physical path of the electron at the slits, the wave instantly collapsed. It completely stopped acting like a probability blur. The electron acted exactly like a solid classical paintball.
Wow.
It went through slit A or it went through slit B. It did not go through both. And the beautiful complex interference pattern on the back screen completely vanished, replaced by two boring, solid, predictable vertical lines.
Okay, that is terrifying. The universe literally changed its fundamental behavior solely because we were watching it.
It is as if the universe knew it was being spied on, realized the jig was up, and immediately put its classical mask back on to hide the quantum weirdness.
And this poses an incredibly eerie implication. Does the conscious, subjective act of observation fundamentally change physical reality? Does human awareness literally force the mathematical probability wave to pick a definitive state?
Or, to take a slightly less mystical, more mechanical view, is our measuring equipment just so inherently clumsy that the act of bouncing light off the electron to see it mathematically destroys the delicate wave state?
This is the exact debate that still fractures physics and philosophy today. The Copenhagen interpretation, heavily championed by Niels Bohr and Werner Heisenberg, leans toward the profound. They argue that the particle fundamentally does not have a defined objective state or location until it is measured.
The act of measurement itself forces reality to solidify.
Exactly. The universe exists in a state of suspended animation, a superposition of maybe, until an observer forces a yes or no.
But others push back on that, right? They say consciousness has nothing to do with it.
Yes, other physicists argue it's merely a mechanical issue of entanglement or interference. To see an electron, you must hit it with a photon. Hitting an incredibly fragile, delicately balanced probability wave with a high-energy photon is like trying to measure the exact position of a spinning top by hitting it with a bowling ball. The measurement inherently destroys the system.
But regardless of whether it is consciousness or clumsy machinery, the conclusion is inescapable. In the quantum realm, you cannot observe a system without fundamentally and permanently altering it. The observer and the observed are completely, inextricably linked. We are not passive audience members watching the universe. Our presence actively shapes it.
Which perfectly, and somewhat terrifyingly, leads into the second massive philosophical headache we need to discuss.
The end of destiny.
Yes. Let's talk about Pierre-Simon Laplace and classical determinism. For centuries, the ultimate dream of science was total, absolute predictability. Laplace proposed a famous thought experiment involving a super intellect, which we often call Laplace's demon.
Okay.
He argued that if this theoretical demon knew the exact position and the exact momentum of every single particle in the entire universe at one specific moment in time.
And if it completely understood all the physical forces acting upon those particles.
Right. If it knew all the variables, it could use Newton's laws of motion to perfectly calculate the entire past and perfectly predict the entire future of the universe.
It is the ultimate, purest expression of a deterministic universe. In Laplace's view, the universe is just an impossibly vast, incredibly complex clockwork mechanism. Once the universe was wound up and set in motion at the dawn of time, every single subsequent event was locked in.
From the chaotic formation of a galaxy, to the exact moment a raindrop hits your windshield, to the specific complex thought you are having right now, everything was preordained by the initial physical conditions of the particles.
In classical physics, destiny isn't magic. It is just a really, really complicated math problem waiting to be solved.
But the quantum blur completely and utterly obliterates Laplace's demon. If de Broglie is right and the double-slit experiment proves he is exact, simultaneous certainty is mathematically impossible.
You cannot know the exact position and the exact momentum of a particle simultaneously because it isn't a solid point. It is a smeared-out wave of probability. If you know its momentum precisely, its wavelength stretches out, and its position becomes a complete blur across space.
Heisenberg codified this in his famous uncertainty principle. It's a fundamental limit of reality, not a limit of our technology.
So if the fundamental microscopic building blocks of the universe are inherently probabilistic, fuzzy, and unpredictable, does that mean the future is genuinely unwritten? If an electron's path is decided by rolling a quantum pair of dice at the moment of measurement, does this mathematical uncertainty at the subatomic level bubble up to the macroscopic level? Does quantum mechanics essentially prove the physical existence of free will?
It is an incredibly seductive thought, and one that many philosophers have latched onto. If the universe at its core is a game of chance, which, famously, Einstein violently hated, stating God does not play dice, then strict Laplacian determinism is definitively dead.
However, we must be careful not to jump to comforting conclusions too quickly. Just because quantum events are random and probabilistic does not necessarily equate to human free will.
A roll of the dice in a casino is unpredictable. But you, the roller, do not consciously control the outcome of the dice. Randomness is not autonomy.
That's a very sobering point. Random chaos doesn't mean I am driving the car.
Exactly. Still, the quantum reality undeniably leaves the door open. It removes the suffocating, claustrophobic physical constraint of a predetermined clockwork universe. It means the future is not a locked script resting in a vault. Reality is being continuously calculated and resolved in real time.
It gives us breathing room. It means there is space for surprise. But speaking of scaling things up, the final philosophical ponder from our deep dive today asks us to scale this madness up to the absolute cosmic limit. We know the math. Lambda equals h over momentum. Wavelength applies to anything with mass.
So I have a mass and a velocity, therefore I have a wavelength. You have a wavelength.
The Earth orbiting the Sun has a specific wavelength. The massive Andromeda galaxy spinning through the void has a wavelength. They are unimaginably, functionally tiny in our daily lives, but mathematically they are non-zero. They exist as waves.
Which means if you extrapolate the mathematics of de Broglie to its ultimate logical conclusion, the universe is not a massive container filled with separate, distinct, isolated physical objects. That is the classical mirage. Instead, the entire cosmos is one infinitely complex, unimaginably vast, constantly overlapping wave equation.
Every single particle in existence is a vibration that extends out across space and subtly mathematically interacts with the vibrations of everything else. The sharp physical boundaries we see between objects, the boundary between your hand and the desk, are illusions born of our limited perception. At the fundamental quantum level, everything is deeply mathematically entangled in a single, continuous cosmic symphony.
A single cosmic symphony. I think my brain has officially reached absolute maximum capacity.
Mine too. What an incredible concept to try and internalize. Let's do a rapid recap of the incredible journey these materials took us on today. We started with the absolute identity crisis of light Newton's solid corpuscles fiercely fighting Thomas Young's rippling water waves until Einstein stepped in and proved it was mysteriously both.
Then Louis de Broglie, our French aristocratic radio operator, steps in with the utterly absurd thesis that solid matter must also be a wave. He gives us the equation of the blur, lambda equals h over p, unifying the ethereal world of waves and the physical world of particles.
We saw how that brilliant little equation perfectly explains the macroscopic mirage, why massive, heavy objects like us appear reassuringly solid, while nearly weightless electrons devolve into blurs of pure probability. We explore the utter madness of the double-slit experiment, watching single electrons take multiple paths and interfere with their own existence.
We learned how those smeared-out probability waves form the rigid 3D standing wave orbitals that dictate the unbreakable geometric rules of all chemistry. And finally, we saw how this invisible quantum behavior is not just theory, it is the physical engine that powers our electron microscopes, our smartphones, and the neon lights illuminating our cities.
It is an overwhelming, breathtaking amount of reality-breaking information. But before we sign off, I want to leave you, the listener, with one final, deeply provocative thought. Something for you to chew on that builds entirely on everything we've discussed today.
I love this part.
We talked a lot about standing waves in chemistry, how an electron's probability wave must perfectly synchronize, wrapping seamlessly around the nucleus so that the crests meet crests and the troughs meet troughs. We established that if the wave doesn't perfectly synchronize, if it clumsily overlaps with itself, it results in destructive interference. It literally cancels its own existence out. It becomes mathematically forbidden. Only perfectly constructive, harmonized waves survive long enough to form the solid structure of our atoms and therefore our universe.
It is a fascinating, almost poetic mechanism of existence dictated by harmony.
Right. So I want you to take that concept of waves surviving through harmony and scale it up to the human brain. Your brain is a massive, incredibly dense network of billions of neurons. And all of those neurons are constantly communicating via electrical signals, which are, at their core, just quantum interactions of electrons and ions moving around.
Yes.
If the rigid physical structure of our universe is entirely dictated by subatomic waves that must perfectly synchronize to avoid canceling themselves out, could human consciousness itself, the profound way we form a clear, coherent, singular thought out of millions of chaotic firing neurons, simply be an emergent property of perfectly constructive wave interference happening in the brain?
That is a genuinely staggering proposition. You're essentially suggesting that a clear thought or a memory is, at its physical core, a macroscopic standing wave of probability stabilizing inside the neural network.
Exactly. And conversely, what about when we are utterly confused? What about the feeling of cognitive dissonance or the struggle of holding two contradictory ideas in our head at once? Are those confusing, fleeting, frustrating thoughts just quantum destructive interference happening in real time in our minds? Is the feeling of confusion literally just our neural waves failing to perfectly align, clumsily overlapping out of phase, and canceling themselves out before they can resolve into a coherent, permanent memory?
It brilliantly bridges the gap between abstract quantum mechanics and subjective neuroscience in a way that is incredibly poetic. If we are fundamentally made of interacting waves, it stands to reason that our very consciousness operates on the exact same universal rules of resonance, harmony, and dissonance.
It's certainly something I'm going to be thinking about every single time I stand in the kitchen and struggle to remember where I put my car keys. I'll just blame it on a little destructive quantum interference happening in my hippocampus.
That's a perfect excuse.
And with that mind-bending thought, we have to wrap up this deep dive. The next time you sit down, reach out, and confidently punch your solid wooden desk, I hope you feel a little less certain about what's actually pushing back against your knuckles. Remember that you are not simply a collection of tiny, solid billiard balls. You are a complex, beautiful symphony of overlapping waves, quietly rippling your way through the cosmos. Keep questioning your reality, embrace the quantum blur, and we'll see you on the next deep dive.